Thank you. Thanks for a wonderful introduction, and thanks to everyone for this opportunity to share some of my work with the HCI group. So, as you probably see from my slides, the, the work I'm going to present is joint work with some of my former colleague and former student. This is about like a preference guided product design with a conditional gain. And some of you might wonder, oh, why we choose this particular architecture. We will talk about this in a minute. So the main point is we try to integrate the consumer preference and user generated content into the design architecture. Uh, Let me move to the outline. So from the high level, so here's the sort of kind of roadmap of my presentation. So I will start with the motivation and the gap we try to address. Then I just walk through the framework architecture and some of the technical details, the prediction model and our modified CZ gain. I will show our empirical application with a real company and present some results from multiple evaluation methods and close with a discussion of our architecture choice and also like the connection with the human computer interface related research. So start with the kind of the motivation. It's actually pretty straightforward, as some of you probably, all of us, I guess, like generative AI has created, enormous excitement for product design. Many tools like Stable Diffusion, Mirror Journey, all these things. Many of us know that the design to explore the ideas much faster than the traditional methods. On the right of this slide, you can see these wedding helmets concept generated through some iterative promoting. This example, actually comes from McKinsey company report illustrating how the generative AI can rapidly produce high fidelity the concept images. But here is like a critical gap. In my humble opinion, consumer preferences are not systematically incorporated during like the design generation stage. Right now, the preferences are used either before the generation to analyze the consumer needs or after to predict the demand for design that have already been created. During the generation itself, the process is somehow ad hoc. A design might promote, make it, let's say, make it more modern, but that's not driven by actual consumer data. The result is that the companies that generate the designs, then they have to screen them through expensive consumer testing to find out which ones the kind of people actually like. So here we try to kind of describe make through this like the diagram to make this gap a little bit more concrete. We have sort of kind of three-stage pipeline: analyze consumer data, generate the design, predict the demand. The consumer preference inform the first and the third stage, but the generation stage in the middle operates without preference guidance. The consequence would be quite costly from the business perspective. For example, in the automobile industries, firms conduct the same clinics where like a consumer evaluate the design concepts. A single vehicle design test cost over $100,000, and this happens after the design are already created. So you're sort of kind of spending more than six figures to potentially learn that your design under a bidding. So our framework try to kind of flip this. We generate the design that are preference aligned from the beginning. So another thing, meanwhile, there's a vast kind of amount of the design relevant information that companies aren't using. For example, the so-called user-generated content on social media and image sharing platforms. we can see examples on the right here, like some of the travel photos on Instagram, artistic shots on Flick, or lifestyle images shared by everyday users. So those kind of UGC user-generated content naturally contain two things we need. First, the rich design features, for example, diverse visual styles that go beyond what any kind of single company has internally. Second, the revealed consumer preferences. So when a user takes a photo in front of, let's say, graphic wall and post it online, they implicitly revealing their that they like that particular visual style. That's sort of kind of preference signal. So existing literature use the kind of user-generated content almost entirely for descriptive purpose. For example, mining reviews, predicting demand. So what we try to do is mostly kind of prescriptive. We use user-generated content to direct generate new designs. That's in our opinion, sort of kind of qualitative shift. Um, and also, let me move this next. Yeah. So there's additional kind of challenge, especially relevant for I would say like a human computer interface community, thinking about deployable systems. Developing or training a generated AI algorithm requires a large database, but small or startup companies, they often don't have enough internal data to learn what their consumer really prefer. This is a classical kind of cold start problems, well known in recommendation system, etc. And our solution is to try to leverage the external UGC as a complementary data source, the external design, expand the training set, and the external preference that reveal choice of the users on the social media can help the model learn what features are appealing even when the internal data is relatively sparse. So that leads to our sort of kind of research question. So essentially, three questions we try to answer. First, how to systematically incorporate the consumer preference into the generative process. So we produce a peeling design ex ante before testing. Second, how can firms leverage the rich design and preference data in the UGC, especially when they face code start issues? And thirdly, how to automate these entire pipelines in a systematic and scalable way. And importantly, we want to have like a framework that is architecture free, one where the preference integration logic is independent of specific generative models. And we use CC gain and DC gain to illustrate, but the pipeline works with any kind of generator. So in that regard, of course, there's large, I know there's a huge sort of kind of literature in computer science, machine learning community for a sort of kind of direct link of our specific context, especially within the product design, within the marketing and business literature. I just list several papers here. And of course, I might miss I mean, in the paper, we of course cite lots of other papers. For anybody here in the audience, if I miss one of your papers here, don't get annoyed. So we sort of kind of the three papers related here. One is by Brunel in the marketing science. They trained a predictor model and generated model separately. The predictor scores design, but doesn't guide generation. We sort of kind of integrate the preference directly into the generating process. I mean, Randu, their paper focus on the logo design using variation auto encodes. One specific aspect of the product design, we sort of kind of generate the entire product design guided by the heterogeneous consumer preference. And Liu, their paper kind of mine like a user-generated content, the images to extract the brand perceptions, purely the kind of descriptive. We go from the descriptive to prescriptive. We use the user-generated content to actually try to generate a new design. By the way, if you have any questions, feel free to stop me. Um, ask your questions. So, oops, uh, yeah, yeah, yeah. Okay. So, Yeah, again, I mean, at a high level, our framework has three sort of kind of modules. First, a data integrate. I mean, yeah. Sorry, okay. Anyway, so yes, first like data integration module that use the internal consumer choice data with external UGC data. Second, the preference learning module, a random forest predictor that learns mapping between the consumer attributes and the design preference. Third, a preference like kind of guided generation module. This is a kind of modified CC gain that takes the predicted popularity score as a continuous conditioning labels and generate a design at the specific popularity level. We want to emphasize upfront again, this is like this three module pipeline is architecture free. The CZ gain is just our illustrative implementation, not a requirement. And I will talk more about that. The data integration module and the preference learning module and the conditional logic all work on the same way, regardless which generator sits in the server box. So we sort of kind of could swap in a, let's say, diffusion model, a VAE, or any sort of kind of other generative architecture, and the pipeline logic stays the same. So we planned three model variants to show what each component adds. The baseline is a standard DC gain trained on a pooled internal external design. It generates a new design from random noise. The benefit of introducing external data is that it increases the training set and introduce visual features the company doesn't have internally. But the limitation is also obvious. There's no sort of kind of preference guidance. The generated design are random draw from the learned distribution, not targeted at what consumer want. Uh, the enhanced model adds the kind of internal consumer preference. These steps are like um, train a predictive model on internal choice data, compute the popularity labels for each design, and feed those as a continuous conditional labels into a CC gain. Then instruct the trained generator to predict to produce high popularity designs. The limitation here is that the predictor is trained only on the internal preference. It knows what internal consumer like among internal designs, but it cannot evaluate novel features from external designs. So even if the game learns to produce new styles from external data, the predictor might flag them as unpopular simply because it's never seen these features before. Uh, so the full model here address like this by training the predictor on both internal and external consumer preference. The key insight is that the user-generated content, photos implicitly contain the preference data. The mapping between the consumer's appearance and their choosing background. We extract these and add them to the training data. The underlying assumption, of course, we also validate empirically is that the external consumers who look similar to internal consumers share the similar kind of preference. So the predictor learns to recognize which external features would appeal to internal consumers, and this guides the CZ gain to incorporate those appealing features from both data sources. And notice here, nothing in this kind of flow diagram is specific to gain. The predictor produce a continuous popularity label. Any conditional generative models that accept like a continuous inputs can use them. The architecture-free nature of this framework means we could just drop in a different generator without changing the preference learning and the data integration logic here. Uh, so some of the technical details here. For those who are less familiar with the game, a traditional game learns to generate images that look like training data, but you can't control what type of image it produce. A conditional gain as a label input, you can say generate a golden retriever, and it will. In our case, the label is the predicted popularity score, which is continuous. So we can say generate a design at the popularity level of zero point 0.9 and gets a high popularity design. Uh, Um, so the prediction model takes like three inputs. In our case, we 128 dimension face embodying from OpenFace, a 1000 dimension design embodied from Cafe BVLC, essentially LXNet feature extractor and the display ranking of the template on a screen. Things like the position affects the choice probability. The output is binary. Did the consumer I choose design J? We train a random forest on these consumer design pairs to get a popularity score for any design. We just average the predicted choice probability across all consumer. This gives us like a continuous label between 0 and 1, and that serves as a conditional input for the CC gain. Um, so like here there are two technical challenges. First, like a standard condition gains, they need category variables, but our popularity scores, they are continuous. We use the CZ gain architecture from Dean 2020, which introduced the hard visional discriminated loss instead of requiring exactly label matches. It trains like a discriminate on images near the target label, addressing the sparsity problem. The second, which in our opinion is our key technical modification is in the Dean paper, they use labels like young, angels, and ages where there's no preference ordering. For example, at age 15 isn't better or worse than age 30. But in our case, the higher popularity is better. So we need a model to recognize this ordinal structure. So our solution is just label the weights. I mean, W equals K times Y. So like higher popularity images gets the kind of proportionally large weights in the loss function. So this signals to the algorithm that the high popularity region of the design space is more important. So accordingly, we modified the loss function. So here is a kind of actual loss function. The discriminated loss is the HVDL from Dean paper, 2000 paper, but with our label weights highlighted in here, you can see they appear as multiplicated factors in both the real image and the generated image terms. The generated loss similarly include the label weight. So the effect is pretty intuitive. When the generator produces an image conditional on high popularity label, the loss function penalizes errors more heavily. This pushes the kind of generator to produce a better image in the high popularity region, which is exactly what we want in our application. Okay, so we apply this to a real business. So this is self-operated photo booth chain in China with about 20 locations in shopping malls. On the right side, you can see the actual app interface. Sorry, yeah. Yeah. Um, so essentially, consumer browse the themes like let's say bright color, shadow and the reflections, or maybe flowers and so on. They choose the templates, take the pictures, take the photos, and print them. And the template are the key product for them. So they are startup with limited resources. They hire outside kind of like designers without incorporating consumer preference, so it's quite ad hoc. And they have the classical cold start problem, limited internal data. The internal data includes, I think, just 83 themes with 585 templates, and the complete order history is from roughly like 2019 2,000 consumers, I mean, in our data. That's about the kind of 34,000 consumer template pairs in the data. Uh, Here are some of the actual templates from graphic themes. You can see the diversity of the style within a single theme. These are the backgrounds consumers choose from. Each template is a background without human subjects. Consumers stand in front of them and take the photos. The company ranked the themes by recency with newer themes on the first page. We focus on the graphic theme for our main results because it has enough internal templates and a clear external analog on the social media. So we collect for the external data, we collect 1,375 photos from social media and image sharing sites. The photos of people in front of graffiti background similar to the photo booth setting. You can see, I mean, the examples for both like the graphic theme and the Chinese traditional theme. We pre-process these by embedding out the human subject to get a clean background template and separately cropping the face for the preference model. So these external data serve as a dual purpose. The background adds the kind of design diversity to the game training set, and the person to background mapping provide additional preference signals for a predictor. So here are some of the training details. So for a predictive model, the model one use about remember the company's 34,000 internal pairs. The model two adds the external data for about 35,000 panel pairs total. So both use like a random forest with 100 trees. We sort of can upsample the majority class since only about 11% of the pairs are positive choices. For the generative model, we train per theme. Here we choose a kind of graphite results here. We combine 13 internal templates with 1,375 external ones yielding roughly total is 1,321 after filtering. Because this is still a kind of small training data set for a game, we use diffuse augment from ZOO 2020, which enables high fidelity generation from as few as 100 images. So the output resolution here, I mean, is 128 by 128, and we will talk a little bit more about that later. So, here are some of the results. So first, in terms of like the prediction accuracy, it seems the model one trains on the internal preference achieve 79.3% of the accuracy with a balanced accuracy of 79%. And model two trained on both internal and external preference improved to 80.6 accuracy and 82.5 balanced accuracy. Both substantially outperform the benchmark logistic lasso model. And the false negative and the false positive rates are both around the zero point 0.2 or below, indicating the model reliably predict which templates consumers will choose based on their facial features. So now let's move to the face validity. So before we evaluating like a preference guided generation, we first confirm the baseline DC game produce meaningful like designs. You can see four generated graphic images on the left. They are clearly kind of graphic style with sufficient variety, no mode claps. More rigorously, we retrain the Resonate 18 classified on 100 like, real graphic and 70 non-graphic images. On holdout test set, it achieves 97% of accuracy. When we apply it to the DC game generated image, 99 are classified as graphic. So the generator produce the thematically validated designs. So this is, like one of the most visually, in our opinion, like comparing results because our CT gain use a continuous popularity label, so we can generate a spectrum of design from lowest to highest popularity. So the top row shows the CC gain with internal preference only. The bottom row shows like a CC gain with both internal and external preference. You can see the gradual style shift. For example, the low sort of kind of popularity design tend to have similar patterns and muted colors, while the high popularity designs show more intricate, the colorful compositions. This progression is consistent with what we observe in the actual consumer choice data. Um, So now we want to like kind of illustrate why our label weight modification matters. On the left are the designs generated without label weights. The original CC game from the Dean 2020 paper, they are you can see it's a little bit blurry and less sophisticated. On the right are the design with our label weights. The improvement here is like sharp details, more kind of coherent patterns, and better alignment with the popular styles. This confirms like accounting for the ordinal nature of the popularity label is important in our case. So now we try kind of move to the main performance questions. Do preference guide designs actually resemble what consumer like? So our first matrix is pretty standard distance based. We measure how close each generated design is to known popular templates and how far from unpopular ones using Cafe BVLC embedding. Here, notice this particular metric is independent of our framework. It does not use our predictor at all. So the results are pretty clear. The CC gain with both preference achieves the lowest distance score of 1.14 versus 1.25 for CC gain with internal only, 1.26 for DC gain, and 1.32 for company's original templates. So all our generated models outperform the company's existing design, and the full model perform the best. So then we try kind of use our own prediction models as an evaluation tool to which sort of kind of confirm the same pattern. We normalize the internal original to one, the CC gain with the both preference showing roughly the 9% improvement when evaluated by this prediction model 2. The CC gain with internal only shows just a 2% improvement, and the DC gain actually underperform the originals when evaluated by model 1 because the model 1 can't recognize the appeal of the novel external features. So this demonstrates the key insights. Merely adding the external design data is not enough. You need to also add the external preference data so the predictor learns which external features the consumer actually like. Um, then we validate this using the consumer survey design. We use a real consumer through like an online survey on Credemo with 288 respondents. The setup mimic the photo booth experience. The respondents see 8 templates, two from each of our 4 conditions in randomized order and choose the two they the most want as a photo background. So the template set varies by, across different respondents, different subjects. So here is the survey results. The CC gain with both preference is choosing 33% of the time, significantly higher than the company's own design, which is like 27.8%. The CC gain with internal only gets roughly like a 23.3, and the DC gain gets just 16%. So the confidence interval didn't overlap between the CC gain with both preference and the DC gain, confirming the difference are statistically significant. So the fact that our AI-generated design outperform professional kind of design templates is a key practical finding for us. So the key takeaway here is, first, the preference integration helps. The CZ gain consistently outperforms DC gain. Second, the external preference are important and essential, not just the external design. Third, our label weight modification makes a meaningful difference. And fourth, the generated image shows significantly greater variety than the internal origins. Measured by both entropy and also convex kind of Hall volume metrics, all statistically significant at like less than p-value less than 0.01. We also demonstrate the personalized design generations for individual consumers by replacing the population average popularity level with the individual level labels and fine-tune the CC gain. So yes, again, I want to, return to the question. Of course, obviously, many of you might wonder, this is sort of kind of the elephant in the room, right? Why are we still using GAN in 2026 when the kind of diffusion models dominate like the image generation? So again, our framework is deliberately architecture free. We choose CZ GAN to just illustrate the pipeline because it natively kind of handle continuous labels and works well with a small data set. But the contribution is the preference guided the pipeline itself, not the choice of the generator. Swapping it in a machine backbone is the natural kind of next step, and the pipeline transfer directly. And we choose the CZ GAN for several practical reasons. It natively kind of support the continuous conditional generation, which is exactly what we need for continuous popularity label. It also it's lightweight enough to run on consumer grade hardware, and the inference is a single forward pass, and it works well with a small training data set when combined with diffuse argument. Let's say that, of course, the natural next step is to implement this pipeline with a modern diffusion backbone, either like a SDA or Flux or similar. The popularity labels could condition generations through classifier free guidance or adaptive methods like IP adapter, etc. This would kind of immediately improve the image fidelity and the resolution and the preference learning and user generated the content integration logic transfer directly. Um, Towards the end, I want to kind of highlight a bit in terms of the connection with this audience, in terms of the human-computer interface related research. So first, this is very much the kind of the human AI co-design. So our framework doesn't replace a human designer. It augments them by generating a ranked pool of the preference aligned candidates that kind of designer can just select from or refine and iterate on them. And you could imagine integrate this into an iterative design tool where like a designer adjusts the popularity slider and sees the design space changing in real time. And second, the personalization at the scale, because we can sort of kind of compute the individual level popularity score, the framework supports the kind of generating designs tailored to specific users. This connects to the work on adaptive interface and personalized content delivery. Third, and I would say more broadly, we are trying to demonstrate a new way to use the user-generating content instead of passively analyze what people post to extract the insights. We try to actively use these posts as a design material, feeding revealed behavioral preference directly into a generative system. This has an implication for cross-sourced design and a particular design process. Okay. So let me sort of kind of conclude. If of course, feel free to ask. To summarize, we propose a preference-guided generated framework that integrate the heterogeneous kind of data source learns consumer preferences through a predictor model and guides the conditional generation towards the kind of design that consumer actually prefer. We use multiple kind of evaluation methods like distance measure metrics, prediction models, and consumer survey. All of them consistently show that our generated design outperform existing company's design in both in terms of popularity and also the variety. And our technical kind of contribution modification includes like the ordinal label weight modification to the CC gain and the end-to-end automated pipeline from the low choice data to generate the design and demonstrate the personalization capacity and the architecture free framework. That's the kind of extendable to other generative models. Yeah. Um, I would say that's pretty much it. Thank you. Thanks, everyone.